Archiving started.
Okay, yeah, let's take a look at the Pleiades lab. So, which particular question are you stuck on? Okay, number 6. Oh, okay. Yeah, so you plotted your HR diagram. Yeah, okay, so you don't have any in the upper right. Do you have some that are a little bit sort of like in the middle and off to the right that don't fall right onto the main sequence? Yeah, then go with those. They're not really red supergiants that you would find in the upper right of the HR diagram. And also keep in mind that with the Pleiades, we're seeing it at a distance. So the luminosities might be lower because we still have the distance factor in there than, if we were plotting absolute magnitude. So yeah, go with those 3 stars that are sort of to the right of the main sequence that are not directly on it. Okay, to draw the line. Yeah, I'm wondering if I should just let me make a quick HR diagram here on the whiteboard. Okay. No, you wouldn't connect the dots because they're scattered around too wildly. What you would try to do is like find the general tendency of most of the dots and then sort of draw a smooth line through them. See, I'm going to try to, I don't know, try to draw some dots here. Yeah, usually not that many up there. Oh. I'll do that. I should draw a lot of them down here. Too big. Oops. I'm just going to draw a couple of points here. And then fill it in. Because, most stars are not exactly the same, even though they may have the same luminosity, but then they have a slightly different temperature, or, there are some differences in the stars with how many metals they contain, and that can, how their energy is transported. So if you have older stars or younger stars, they might not coincide exactly, even if they have the same mass. Okay, just filling in a few more dots here. Trying to erase one or the other up here. Okay, yeah, let me pick a different color. So instead of connecting all the dots individually, they're just too many. And like I said, there is a little bit of a variation between the stars. So you would take undo that. Oh, here we go. Okay, that wasn't exactly smooth. I'm going to try to do it a little bit smoother, but that's sort of the idea. Just sort of draw a smooth line through the general tendency of those stars. Okay, let me just make a couple of stars. You have a couple over here. Now those would be your red giants, and then you might have one or the other down here. Which would be your white dwarfs. See, I'm just trying to make an arrow here, which didn't quite work out. Okay, so those would be your red dwarfs. Sorry, red giants. Okay, and then over here, oops, gotta switch it. Okay, so those couple, handful, would be your white dwarfs. Okay, and then let me quickly label the blue main sequence here. Sort of what you're looking at. And you have the apparent magnitude on the vertical axis and the, well, B minus V, which is sort of a color index. On the horizontal axis. So depending on how far or close a cluster is, if we plot the apparent magnitude, if a cluster is very far away from us, much further than the 10 parsecs that the absolute magnitude is based on, then it would be at much higher magnitudes. the main sequence and the red dwarfs, because it would be a lot fainter. And if there's a cluster that would be closer to less than 10 parsecs, then we would get into much lower magnitudes, but you would get overall the same shape of the main sequence and red giants and white dwarfs. It's just that everything is sort of shifted towards larger magnitudes if the cluster is further away, or lower magnitudes if the cluster is closer. Okay, so what's your next question? Oh, okay, so the magnitude in number 10. Okay, if you go to, actually, let me share my desktop, and then I can show you where to go to find the overlay, and that's where the absolute magnitude is coming from. The apparent magnitude is coming from this, this graph that you made with the Pleiades. You could take any point that is easy to read off of the graph. Actually, let me go ahead and make a couple of ticks on this axis here for the apparent magnitude. Of course, they may not be evenly spaced. Doesn't look like it. Okay, so yeah, let's say this is maybe 5 up here. 10. Then 15, 20, okay, 25. So this would be apparent magnitude for the Pleiades. And then, yeah, let me save this real quick and share my desktop. And then I can show you where you get the absolute magnitude HR diagram from that you then put right on top of it. Okay. Okay. So hopefully you're seeing my desktop now. Okay, and I'll need to switch to the 1020 lab. I entered this room from the 1010 lab. It doesn't really matter. I think this is just one room for all of my classes. Okay, switching over to the 1020 lab. Okay, and if you go to Learning Modules, Photometry of the Pleiades, and the lab summary sheets, which is item 4 in the table of contents, then scroll down to Photometry of the Pleiades. Okay, let me enlarge that a little bit. It's kind of hard to see. Well, still might be kind of hard to see, but anyway, you can go down to the last page and print out the last page. And this would be the Pleiades main sequence, plotting the absolute magnitude. So what you would do is you would print out that page and then lay this page with the absolute magnitude versus the color index on top of your graph that you made, match up the main sequences, so that the main sequence on the absolute magnitude HR diagram from the overlay here matches up best with your main sequence, you know, the smooth line that you drew that was closest to all the points, so that those two match up or lie on top of each other. And what you'll find then is that those magnitude scales are different. So if you pick one particular point on the absolute magnitude scale, I mean, you could pick the 0 point here, for example, and then it's like as if you were poking a pencil through that point, and then, okay, it says 0 on the sheet that plots absolute magnitude versus the color index, but then if you poke through and look at what apparent magnitude that intersected, then those are the two magnitude values that you want to write down and calculate the distance from. Because basically it says that if there's a star in the Pleiades cluster with an absolute magnitude of 0, you know, the star would be at this position here, then it would have an apparent magnitude of this other value, you know, that is right underneath it in the apparent magnitude diagram. And it has this different apparent magnitude value because it is at a different distance from us than the 10 parsecs, you know, that the absolute magnitude goes by. So by comparing the absolute magnitude from the absolute magnitude sheet with the apparent magnitude that is directly on the sheet underneath, you write down those two values. Okay, so let me go back to our window and end the sharing. Okay. Yeah, unfortunately, they're not sized the same. Yeah, let me just put that into writing here. So the absolute versus B minus V diagram and the apparent magnitude versus B minus V diagram are not sized the same. So yeah, where you might get a little bit of more of an inaccuracy from, yeah, so that might lead to a little bit more inaccuracy. I know that though, so if you go through the procedure correctly, even if the values that you get are not, exactly spot on, then I'll still give full credit, for all the calculations. So you just try to estimate the best you can. So match up, as in laying on top of the bold line for the main sequence of the absolute magnitude diagram. So on top of your main sequence from the apparent magnitude diagram. And just, slide it up or down or sideways as best as you can. So try to get them on top of each other as best as you can. Then pick an absolute magnitude on the top sheet and look directly at the point underneath and read off the apparent magnitude of that point. So these are your values for the big M and small m in question 10. And it doesn't really matter which point you pick. As long as you pick one and then read the one on top and the one directly underneath. So in general, you should get a difference in magnitudes of about 5. So the difference can be a little larger or a little bit smaller, but it probably maybe a little bit smaller, but it should be close to 5. So the difference may be a little smaller. I'm going to click back to the e-board. Gives us a new e-board. Oh no, okay, it's the same one. Okay, let me try to draw what it would look like with the overlay, maybe in a different color. Okay, so this is going to be the absolute magnitude versus color index overlay. Okay, and you've been trying to match the main sequences as best as possible, so kind of like in the overlay it would look like this. So pretty close, but not exactly. Actually, let me draw that a little bit. I can't see the blue anymore. Okay. So something like this. So that would be the main sequence on the overlay. Okay, and then the tick marks of the overlay might be something like this. Here. It's a little busy right here. So you can see they're all a little bit offset, potentially. Get one more in here. And this up here might be 0, the absolute magnitude of 0. See, this could be 5. $15, $20. Well, the bottom one would be 25 then. Okay, and then you would match up and say, let's see which color I'm going to pick for that, maybe purple. Yeah, let's say you're going to read the magnitude, the apparent magnitude of this star. Oops. Gotta select the pen first. Sorry about that. Because you can pick any point of your choosing, and then you read on both axes what the apparent magnitude and what absolute magnitude that star would have. Okay. So I'm just gonna that's a little off. You can just undo both. And so you go straight across like this. Okay. Let me put a text box with that. Okay, so read M and, well, the big M and the little m for the same star off of both axes. Okay, so in our example, we would get a little m of maybe 4.9 and a big M, or an absolute magnitude, of maybe something like 1. Let's just say 0, because it's just as an example. Okay, and with those numbers, you would plug those into number 10. So those would be your answers for number 10. I'm going to make a little box around that. I'll make a regular box. Okay. That's there. Oh, there it is. Took it a little while. Okay. So, do you have an idea how to go from there, or, I mean, I'll be happy to go over it, the calculation of the distance. Okay. Yeah, let me make a new slide. This has gotten awfully busy. Okay, so I've saved it, so I'm gonna clear the slide and start with a new one. Okay, so that's very large. Okay, so from the previous slide, we wound up with an absolute magnitude so our absolute magnitude, capital M, was equal to 1.0, and our apparent magnitude, lowercase m, was equal to 4.9. So that was our question 10. And then in question 11, there's a formula that will split into two parts. So going to split the formula into two parts. And in fact, that's the same type of calculation that we did for the classification of stellar spectra. So it's exactly the same thing where we calculate the exponent first and then put it to a base 10. Okay, so the first part, let's see, so the first part is the exponent. Okay, let me use a different color. Okay, so that would be m, apparent magnitude m, minus absolute magnitude m, plus 5. Okay, we want to put this in parentheses. Okay, those are not going to be very pretty. And divide by 5. Oops. Okay, so let's plug in our values. So we would have apparent magnitude of 4.9 minus the absolute magnitude of 1.0 plus 5 equal, oh wait a minute, that has to be divided by 5. Okay, and let me just make this all visible and put parentheses in. Okay. Yeah, I'll just continue in the next line here. So 4.9 minus 1.0 would be 3.9. Okay, plus 5 would be 8.9. Ah. Okay, here you go. You're calculating it. Very good. Okay, so we have, thanks so much. Just write this out. Okay, 8.9 divided by 5, which is equal to 1.78. And this is now our exponent. And then we need to use the base 10 with that. Oops, I wanted to make that black, but it didn't quite work. Okay, so the second part would be, see if I can get the writing to be black now. So use the exponent with the base 10. It gets cut off. Okay, so we have equals 10 to the 1.78 exactly. which you calculated to be, 60 point, that sounds about right, 60 point, let's just say 26. And the units would be parsecs. Okay. Yeah, let me just mention that that is the distance. Oops. Okay, save that. Okay, so that would be the distance to the cluster, because all stars in that cluster are at the same distance from us. That's why we could just pick one star and read off its apparent and absolute magnitude, calculate the distance of this one star, and all the other stars are in the same cluster, so they're at the same distance. Yes, exactly. So to convert, so that's question question 11, so question 11. So question 11, continued, convert to light years, and we know that 1 parsec is equal to 3.26 light years. Yeah, you just multiply like you did. So 60.26 parsecs .26 light years, and actually per parsec, so the units of parsecs cancel out and are replaced by the light year units, equals 196.43 light years. Okay, yeah, so that would be the answer, both answers to question 11. Then in question 12, you calculate the percent error. Yeah, which is basically how far off percentage-wise are you from the accepted value of the distance that was potentially measured by other people. Well, the numbers that I used are examples. So you may get different numbers for your own calculations. Let me just write that in here. So remember, so the actual numbers might be different. I mean, the actual magnitude values might be different. So the actual difference in magnitude.
I have a question.
Uh-huh.
A percentage cannot be negative, so even if the answer is negative, we just convert it to positive?
Yeah, you can, well, what you would do, you would just take the absolute value and then indicate in the parentheses behind where you would put the numbers, whether your value is high or low. So if you get a negative value, then your accepted value is higher than the, wait a minute, your experimental value is lower than the accepted value. So if you have a negative value for the percent error, then you would just circle or enter the low, that you were low. see, if your experimental value is larger than the accepted value, then you would get a positive difference. And in that case, you would say that your value was high. Okay. Is 250. Light years, and our experimental value from above is 196.43 light years. Okay, so then question 12. See, ours was low. So you would calculate, actually I can use parentheses, I don't have to draw them, I just noticed that. The experimental value, which was, I'm going to just write out the formula, experimental value minus accepted value, then divided by the accepted value, and the whole thing times 100. So that's your percent error. And just to be sure, I'm going to make another, that wasn't good. Set of parentheses around here. Okay, so let's plug in some values. Yeah, my son has just joined me. Oops, no, I want that blue. Okay. Okay, the experimental value was 196.43 minus the accepted value, which was 250. Okay, and then divide that by the accepted value, which was 250 times 100. Okay, I'm just going to put in the parentheses. Okay. I'd have to pull out my little calculator to confirm that. But yeah, you get something negative, but you're just going to use the positives and then say if you're high or low. So yeah, that's okay. Yeah, in the lab, for the actual value, for our example, we were going to use the 250. I'm glad you realized that. Okay, so just use the positive difference. And well, the positive difference is just like the absolute value. And indicate whether your value is high or low compared to the accepted value. Okay. Okay, so let me put our result in here. Okay, so 21.42%, and then you could say something like low, because we were below 21.42%, below 250. Okay. Okay, I'm battling kids and cats here. Yeah, the cat wants to climb over the keyboard, and my son just tried to get a really heavy bag off of the table. Okay, well, actually, then we're almost done. Just one more question to go. Let's see, did I already save this? I think I already saved that. And let me save it again just in case. Okay, and then clear the slide. So question 13 now. Yeah, what would be the sun's apparent magnitude if it were located in the cluster? Okay, and we know that the star and if you look into table 1 on the previous page, so that would be 19 dash page 9, oops, page 19 dash 8. It gives an absolute magnitude value yes, the G2 is 4.4, G5 is 5.1. Actually, instead of estimating, you could also go to the overlay and look up what the absolute magnitude is there. But if you were to estimate from the table, then the absolute magnitude for the sun would be something like 4.4, 4.7, Yeah, so you'd estimate from the table. So it's absolute magnitude lies between 4.4 for G 0 and 5.1 for G5. So about, see, we estimated maybe 4.7. Well, what you can do now, you can plot, well, actually you can do two things. Let me use a different color. You can plot the position of the sun on the overlay corresponding to its B minus V of plus 0.62 and its apparent, well, let me just say it's lowercase m, uppercase m, the absolute magnitude of 4.7. And on the Pleiades diagram, so put the overlay back. I have to continue that on the next page. Just save that. Okay, and okay, so we have Q13 continued. So we put the overlay back on top of the apparent magnitude versus B minus V of the Pleiades cluster and read its magnitude, its apparent magnitude, off of the bottom, well, the scale, the apparent magnitude scale. And, so this would be one way of doing it, or you could just say, so in effect, or maybe in essence, difference, or let's see, how should I put this? Yeah, the difference between the absolute magnitude of the sun its apparent magnitude in the Pleiades cluster would be the same star in the Pleiades cluster, which is basically what we have already read off in question 10. What would be that difference? Is M from question 10. And I hope this will come out when let me just type that right here. Let's see, we had a difference of 4.9. No, let's see, I think it was 3.9. Yeah, we had 4.9 and 1.0. So in our example, okay, yeah. Yeah, unfortunately, this is not a word editor. Well, let me just type it in the in the chat box, and then I'll see if it came out when I transfer the slide out of Wimba, and if not, then maybe I'll make a new slide with smaller writing. Okay. Yeah, so what it says, basically, you can apply the same in magnitudes to the sun as you determined in question 10 for the Pleiades cluster. So in our example, the difference was 3.9 between apparent and absolute. But of course, in the actual experiment, you should get a number closer to 5, that the difference in magnitude is closer to 5. And in our example, I just made up these numbers, so they're a little bit different from what you actually get. Okay, so with an absolute magnitude of the sun of about 4.7, that would put it at an apparent magnitude of 4.7 plus 3.9, which is about, 8.6. But again, remember that I use different numbers for our example. As you would get in the actual lab. Okay. course, another way you could do it, and b is equal to 10, and then to the exponent, lowercase m minus uppercase M plus 5 divided by 5, and just, well, solve it for the apparent magnitude, and then plug in the absolute magnitude and the distance. But of course, that would be the most mathematical way, but it should give you the very similar answer to the two ways I just explained on the slide. Let's see, do you have any other questions? Okay. All right, yeah, let's wrap this up then, and I see if I can post those slides and maybe complete them in that particular learning module and also on the discussion board. Okay, well, have a good night. And thanks for coming.